So we're going to talk a bit here about applications of exponential and logarithmic functions. So dealing with exponential functions and logarithmic functions in an application setting, meaning word problem. We have already discussed exponential growth, talking about like money being compounded nthly. So today we are going to talk about continuous exponential growth. So when you see words like continuous, exponentially, population, half-life, those are all going to indicate to us we're going to be dealing with this PERT formula over here. So it looks very similar to our interest compounded nthly, but for compounded continuously, we use P representing our principal or initial amount. Notice I have an alternate form over here. We use P sub 0 or P naught. That's just kind of a more sciencey way of writing it. We've got R, which represents our rate. Now remember that rate needs to always turn from a percentage into a decimal. An example of that, 5.2% would be 0.052 as a decimal. And then we have T representing time. So my independent variable is T. I'm going to plug in a time, and my dependent variable is A of T, my end amount at time T. So again, this other formula, A of T equals P, e to the kt. They're just using K instead of R for rate. Variables are interchangeable as long as you know what they mean. And then the sub 0, that just means our initial amount. That means P at T equals 0. And the only thing that we really need to remember here is that when we start dealing with things that are decay, things that are declining or deteriorating, the rate must be negative. And what we need to remember is that the function won't always be given. So you need to make sure you read that problem carefully, because if it says that something is decaying, you're going to need to put the negative in your function. So, and as I said, we use this for money compounded continuously. When we see population, growth or decay, we see that word exponential or half-life. All of those words indicate we are going to use that PERT formula. I do want you to remember that we talked about this. We talked about money compounded nthly, like monthly or daily. And in those situations, we would need to use this formula. So if you see some time that is finite, some quantity of time that you can put a number on, that you're going to need to use compounded nthly. But if we're talking about money and it says continuously, what kind of number can you put on continuous? You can't. So continuously we'll use PERT. So let's do a problem here. So what we have a word problem. It says, under ideal conditions, a population of rabbits has an exponential growth rate of 12.7% per day, considering an initial population of 100 rabbits. So the first thing we're asked to do is to find the exponential growth function. And I see those words, population and exponential, and that lets me know I'm going to use my PERT formula. So I know what my initial amount is, and I know what my rate is. My rate, 12.7%, R is 0.127. So make sure you take that percentage, even if it already has a decimal in it, and divide by 100. Percent means per 100, so divide by 100. So my formula here would be A of t, my end amount at time t, equals, my initial population is 100 rabbits. So I've got 100 e to the 0.127 t. So this represents my function. And it's very important to remember when we write a function that we have an input t and an output a of t. So we have an independent variable x and an output variable f of x or y. All right? So we need those variables in there. One mistake I find is students will start reading through the problem and they will plug a value in for t too soon. And if you do that, you're missing a key part of this, this portion of the problem, because it says you need a function, and a function has to have an input and an output. Okay, so we're going to graph the function. We're going to go to our y1, and you want to type into it 100, use your E button, and then you're going to raise that to the 0.127 x. Get that arrow a little bit out of there. Okay, and you need to make sure all of that is in the exponent. So if your calculator is not creating that little tiny exponent, doesn't have the math type feature, you're going to need to use these parentheses correctly. And if you graph that on your standard 10 by 10 window, you're not going to see anything. So you need to think about how to change the window on your calculator. Remember, you have a window button. How to set your X and Y so that you can see this. So thinking about a graph, when we graph something, we measure generally time on the x-axis, and then our output in this case is the population. This is our bunnies. How many bunnies we have. So we're dealing with time, and we don't really know what a reasonable amount of time is, but the rate is per day. So I'm going to do my time, t in days, I'm going to set that at maybe 30 days. So I'll change my window so that my x-min is 0 and my x-max is 30. And then my bunnies, how many bunnies do we start with? We start with 100. So that means it's growing, right? So we're going to have to see up above 100. So playing with your window and looking at the graph, you're going to need to choose a y max, that highest y value, to be something bigger than 100. And, there are a lot of values. You could pick 1,000. Okay? And so we know also that we can leave off quadrant 3 and 2 and 4 because the values for my output are never going to be negative. I'm not going to have negative bunnies or negative time. So doing this on my calculator, I get a graph that does something like that. And we know that y-intercept is at 100 because that's how many bunnies we started with. Okay? So, as you're graphing, just think about a way to create your window. And that might not be the first choice, or your first choice, I should say, might not be the best window. But it's really up to you to think about the variables and the quantities and choose your x-min, x-max, and your y-min and y-max. Okay, so now we have our function, we have a graph. We can continue with our problem, and we're reaching the real meat of the problem here. So I'm just going to rewrite my function. We're dealing with a of t equals 100 e to the 0.127 t. It says find the population after 2 weeks. So we want to know the end population, my a of t, after 2 weeks have passed. So does that mean t equals 2? So remember, the rate is 12.7% per day. So we need to take that 2 weeks and turn it into 14 days. And in this situation, we're just evaluating that function a of 14. So we have 100 e to 0.127 times 14. And if I plug that in, my output is 591.8. Now, this problem says round to the nearest whole number. So rounding the way we've been taught, we would round that up to 592. But we're just going to think a little bit realistically here. Can you have 592 rabbits? Do we have 592 whole rabbits? And the answer is no. So rounding logically, we're going to say that there are 591 rabbits. That population sure did multiply like rabbits. Okay, so one more question here. How long will it take for this to double? So again, we still have a of t equals 100 e to the 0.127 t. That's my function. So if we want to deal with it doubling, that means the 100 that I'm starting with needs to become 200. So in order to think about solving this, I would say 200 equals 100 e to the 0.127 t. So now we have to solve an exponential equation. I can divide by 100 on both sides, and 200 divided by 100 gives me 2. In order to solve this exponential equation, I would then take the natural log of both sides. So taking the natural log of e is going to cause that to cancel, and now I have the natural log of 2 equals 0.127 t. And I can divide by that value on both sides, and I'm going to end up with natural log of 2 divided by 0.127 equals t. So that is my exact point when I will have double rabbits. And if I type that into my calculator, I'm going to get that t is approximately 5.457, we'll say 85 days. So this says round to the nearest whole number. Following, our rounding, that would round to 5. But at the start of the 5th day, would we have double rabbits? So if we were rounding to the nearest day, that nearest whole number, in this situation, that would round up to by the 6th day, we could say. Now, when you're working on your homework on the computer, you may need to round to a whole number, and the computer isn't going to expect you to use this logical reasoning. It's going to expect you to round the way you've been taught to round. So technically this would round to 5. But at the beginning of the 5th day, we wouldn't have double that rabbit population. It wouldn't be until somewhere during, halfway through the 5th day. So we've talked about exponential population continuous growth, and we've done an application problem.